So last time we have seen examples of normal subgroups. Today we will be doing an example of a subgroup that is not normal. And also we will be looking at two theorems regarding normal subgroups. First of all, just like I said, the first thing that we will learn is example of a subgroup that is not normal. It is best if you can remember this example. So the example is this. Okay, we have to take, again, if you give an example in group theory, first of all you have to mention the group S3. Okay, so what is this S3? We have learned that S3 is this group E 1 2 1 3 2 3 1 2 3 and 1 3 2. Okay, next, okay, we have to give an example of a subgroup that is not normal. Okay, so we have got the group, and the operation is of course the composition of cycles. Now let us see what will we take the subgroup. Again, this one you will have to remember. You will take it to be E equal 1 2. First of all, let us see if we have to show that H, it is a subgroup but it is not normal. Okay, so the first part is proving H is a subgroup. Since we are having a finite number of elements, there are only two elements, so it is best if you can create the composition table. Okay, so over here we'll be having E, and the other element is 1 2 E 1 2. Okay, E and E will give you this. Okay, you can actually verify it. You already know how to compose cycles, so you will get this. This is the composition table for this subgroup only. Okay, so if you compose any two elements, result, this is the result. These are all the possible results. So you will see that all these elements in the results will be in H. Okay, so the first condition holds. Clearly, from the composition table, for any AB belongs to H, for all A, B belongs to H. Okay, so no problem at all with the first one. Now let us take a look at the second one. Also H is non-empty. All right, that is actually the first one. H is non-empty. Okay, this is the second one. Now we just have to prove that the inverse of each element of H is also an element of H. If A equal E, then A inverse equal E, which also belongs to H. If you take A equal 1 2, A inverse, it will be the reverse. Okay, it will be the reverse of 1 2, which is 2 1. So this one, it looks like it is not in H, but remember the cyclic order of a cycle, 1 2. Okay, so you are writing it as 1 and 2. If you maintain the cyclic order, it will be the same. That is 1 2 will be equal to 2 1. Okay, because we are still maintaining the cyclic order. So this is 1 2. Okay, so what can we say from all of this? We can say that hence A inverse belongs to H for all A belongs to H. If you take A belongs to H, you are getting A inverse belongs to H. If you take another A belongs to H, you are getting A inverse belongs to H. Alright, so hence A inverse belongs to H for all A belongs to H. Okay, hence H is a subgroup of G. Okay, now we will show that H is not normal in G. Okay, so how will we do this? If you remember the definition of normal, I will write it over here, maybe with another pen. This is not part of the proof, it is just a recollection. The second condition was GHG inverse belongs to H for all G belongs to G, H belongs to H. Okay, so this this definition we will use when we have to prove that a subgroup H is normal. Okay, but now we have to show that it is not normal. So what will we do? Okay, so the possible values of H are E and 1, 2. Okay, these are the possible value of H. Okay, because as you see, this is the subgroup H. So if you take H from this, so the possible values are E or 1, 2. Okay, so these are the possible values of H. What are the possible values of G? The possible values for G, okay, they are all those things, that is E, 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3, 2. Okay, similarly you can find G inverse, the possible values of G inverse, the inverse of this one is E, inverse of 1, 2, it is 2, 1, but we can write it as 1, 2, again this one is 3, 1, or 1, 3, and so on. Okay, so we have different values for G, different values for G inverse. Okay, but if we take G equal 1, 3, okay, just see G 1, 3 is still in G equal 1, 3, it is still in G, H equal 1, 2, it is in H, we get G inverse, G it is 1, 3, H it is 1, 2, G inverse it is 3, 1, okay, the inverse of this one it is 3, 1. How much will you get? Okay, if you calculate this one by using a composition of cycles, okay, you will have this. Okay, so ultimately what you get, you will get 2, 3. Okay, but 2, 3 does not belong to H. 2, 3 does not belong to H. Just refer what is capital H. Okay, you will have this. So what have we seen? We have seen that for some value of H and for a particular value of G, G inverse does not belong to H. Hence, H is not normal. What can we say from over here? From here, actually, the value of G that you take depends on you, and the value of G inverse that you take will depend on you. But sometimes you may have belongs to H. Okay, if for all possible values of G, if for all possible values of H that you take, you are always getting G inverse belongs to H, then you can conclude that it is not normal. But if for some particular value of G and for some particular value of H, you are getting G inverse does not belong to H, then we can conclude that H is not normal. So I think that is clear. So now let's take a look at the first theorem. So the theorem, the statement is H is normal in G if and only if G capital H G inverse equal to H. So over here, because we have this word if and only if, so there will be two parts to the theorem, the direct way and the converse. Okay, so let's prove the direct way first. Okay, the direct way is we have to assume let G inverse equal to H. Okay, we assume this. What do we have to prove? We have to prove that H is normal. Okay, but before going into the proof, because we are involving this one, G inverse, what is it? Okay, because we haven't encountered something like this. Okay, we have encountered cosets, but we have not encountered something that looks like this, where we are multiplying a subgroup by a G and G inverse from the left and from the right. Actually, this reminds me. Let H be a subgroup. H be a subgroup of G. Okay, the statement should be like this: let H be a subgroup of G. H is normal in G if and only if G inverse equal to H. Okay, all right, so let us come back to this. So this one, it's also a set. Okay, if it is a set, it consists of all element X which is of this type. X will have to form G inverse such that H belongs to H. Again, I forgot something here in the theorem, which is for all G. For all G belongs to G. All right. Okay, so this set G inverse, it has this form. It consists of all elements X, which has this form, which can be written as an element of G times the element of H times the times G inverse. Again, in between, it is the operation of the group. Similarly over here, okay, you can think of it as the operation of the group. Okay, so I think this is also clear. Now let us get back to the proof. Okay, so H is normal. We have to prove that H is normal in G. Okay, so let's see. If we have to prove that H is normal in G, we always have to follow that procedure. It's kind of a procedure. First of all, we have to show that H is a subgroup, and then we prove the second part will be proving the normal condition. Okay, so the part one is proving H is a subgroup, but that is already given. Subgroup of G. Okay, but that is already given. But that is given in the okay, because it's already given that let H be a subgroup of G. Okay, so that is already given, so hence we don't have to do number one. Okay, now we'll just move ahead with number two, that is proving the normal condition. Proving the normal condition. Okay, so how will we do it? Okay, so we'll start with let G belongs to G and H belongs to H. After a few lines, we need to get G inverse belongs to H. Okay, so over here, G inverse, where does it belong to? This element, it belongs to the set G capital H G inverse. Just see. Any element of this type, belongs to the set G inverse. Okay, so that is why I'm writing it belongs. Maybe we have this element belongs to G capital H G inverse. But G inverse, it's equal to H. Okay, it's given. So let's see. This is what we are doing in the first part of the proof. Let G inverse equal to H. Okay, so that is why this line, okay, so it belongs to H. So actually in only two lines we have been able to get this one should be small h. Okay, so we have got the normal condition. Okay, it doesn't require much work. Okay, hence H is normal in G. Okay, so the first part, it is straightforward. Next, what we will do, we will prove the converse. Okay, proving the converse, we will have to assume that H is normal in G. Okay, maybe let H be normal in G. Okay, we have to prove G inverse equal to H. Okay, so how will we prove this one? if whenever in group theory or in ring theory, okay, as you will soon find out, or anywhere in fact, if you see sets and if you have to prove equality of sets, remember what we did in the first semester. In the first semester, if we have to prove the equality of two sets A and B, we first have to prove that this one, it is a subset of this, and the second part will be proving H will be a subset of this one. Okay, so that is why we'll divide it into two parts. Again, part one will be proving GHG inverse subset of H. Okay, so how will we do it? If you remember the first semester, we have to take an element of this set. Let X belongs to G, capital H, G inverse. Okay, since X belongs to that, so we can write it as GH, G inverse. Okay, H, small h now belongs to capital H. If X is an element of this one, we can easily replace that capital H by small h, so that it will be an element and no longer a set. Okay, but because H is normal, how do you know that H is normal? Because the second part we have assumed that H is normal. All right, so since H is normal, this one belongs to H, since H is normal. If H is normal, GHG inverse belongs to H. All right, hence GH, G inverse is a subset of H. Okay, part 2. Okay, part 2 for the converse. Okay, proving H is a subset of GH, G inverse. Okay, so how will we do it? We will write it in this way. Okay, we can write it with X or we can write it with H, it doesn't matter. So we'll start with that H belongs to H. We will have to get that this H after a few lines that it also belongs to GH, G inverse. Okay, but H, it can be written like this. It can be written as G, G inverse, H, G, G inverse. Okay, how do you know that we can write it like this? Okay, maybe I should have written it in a better way first. Okay, I'm writing it like this. EHE. H is equal to EHE because if you multiply with the identity, it doesn't change. Okay, so actually, what I want to do is, I want to write H in this form. G, and then an element of H, and then an G inverse at the end. So that's why I've just introduced G from the first, from the beginning. But then we have to write G inverse so that it won't change. G inverse will be equal to E, H, G inverse, G. Okay, so we can write it in that way. All right, it doesn't change because we have multiply G and G inverse. Okay, G inverse will give you E. Okay, so this one will be G. It can be written in that way. G inverse, H, G, G inverse. Okay, so this one, I can write it. It belongs to G, H, G inverse. How do I know that it belongs to G, H, G inverse? First of all, this one, it is G, this one, G inverse. Okay, it doesn't make any difference. So, but this one, if you see, so the reason for this one is, since G inverse, HG, it belongs to H. Okay, G inverse HG belongs to H because H is normal. Okay, if it is normal, always remember the inverse H times G will belong to H. Okay, hence, since H will be a subset of GHG inverse. Therefore, ultimately from part 1, part 2, H equal GHG inverse. Okay, so this completes the proof. Okay, we have managed to prove the direct way and the converse as well. Okay, so do not worry. Okay, I will write the proof down properly and I will send it to you in the WhatsApp group. Okay, so while we still have time, I will do the second theorem, theorem 2. Theorem 2, it says like this: let H be a subgroup of G, then H is normal in G if and only if every left coset is a right coset. Okay, so this is the second theorem. Okay, so let's see. Proof. Again, the direct way first. Let every left coset be a right coset. Okay, we have to prove H is normal. Okay, so how will we start? So because we are given that every left coset is a right coset, we have to show that H is normal. Again, if we have to show that H is normal, uh, we need to prove those two things, but since we already have theorem 1, let us try to use theorem 1. So let's see. We have GH is a left coset provided G belongs to G. All right, so what do we have from the given statement? The given statement says that every left coset is a right coset. This left coset, it is a right coset. Okay, some of you may be thinking that we can easily write it down as this one, left coset is equal to right coset. But actually, there is a mistake with concluding this one directly. Of course, after a few lines, we will get this one, but for now, we cannot do it because the statement, it just states that it is a right coset. It doesn't say which right coset it is. So that's why I will write it as maybe hx. Still, if gh is a left coset, it is a right coset. We still haven't known what this value of x is. All right, it may be or it may not be equal to g. Okay, but ultimately we will get x to be equal to g. All right, so let's see. So left coset, it is a right coset. All right. Also, we have G belongs to GH. Okay, maybe I will write it down this way first so that it will be more clear. G equal GE. All right, we can write it in this way. And GE belongs to GH since E belongs to H. Since E belongs to H, so GE will belong to GH. All right. Okay, so just write this one as equation 1. Also, okay, but GH is equal to HX. Okay, but we have GH equal XH. Okay, but we have that. Hence, GH equal HX. Okay, hence Hence G, since it belongs to GH, so it also belongs to HX. Okay, name this one as equation 2. All right, but also G, it belongs to G. It can be written in this way. It can be written as EG, sorry, E small g. This clearly belongs to HG. It belongs to HG since E belongs to H. Okay, since E belongs to H, so G belongs to HG. Equation 3. All right, name this one as equation 3. From 2 and 3, G belongs to HX and G belongs to HG. Okay, so HX intersection HG, it is not empty. Okay, so why are we bringing this condition here? Because if you remember, we already have a theorem about cosets. All right, once you have HX intersection HG is non-empty, we can conclude, therefore HG will be equal to HX. Okay, maybe name this one sorry. Hence we can conclude GH is equal to HX, but HX is equal to HG. Therefore GH is equal to HG. In fact, we can go another line multiplying by G inverse to the right. Okay, what will we have? GH G inverse equal HG G inverse. Okay, so we can say GH G inverse equal H. If GH G inverse is equal to H, by the first theorem, we can conclude by theorem 1, we can get H is normal. Okay, because theorem 1 says that once GH G inverse is equal to H, we can easily conclude that H is normal. Okay, so this completes the direct part of the proof. Okay, now we will do the converse. Okay, the converse will have to start with that H be normal in G. We have to show every left coset is a right coset. Okay, since we have to show that every left coset is a right coset, what we will do, we will start with a left coset. Let GH be a left coset. Okay, maybe GH be a left coset. After a few lines, we have to get GH equal to some right coset, HX or HG. Okay, whatever. All right, we just need to conclude that every left coset is a right coset. It may be equal to HX or it may be equal to HG. Doesn't really matter. Okay, so how will we do it? Since H is normal, we have by theorem 1 we have GH G inverse is equal to H. Okay, so by theorem 1 we have that. So GH G inverse, you multiply it with G on the right hand side, so we'll have this. So GH G inverse times G will give you E, that is GH equal HG. So a left coset is equal to a right coset. We have started with let GH be a left coset. Ultimately, we have got that GH, which is a left coset, it's equal to a right coset. Hence, every left coset is a right coset. Okay, so this completes the proof. Again, I will write it down, but I think that is enough for now.